Swayam Prabha. Digital India. Educated India.
So let's start our discussion today. We're going to talk about largely about dependent analysis and loop transformations. And you're going to have an exciting set of lectures by Professor Sanjay Rajobhadai next week. And this is going to be in some sense the preliminaries or the basic background for that talk. So look at it from that perspective. Again, I may have more slides than what I can cover in an hour. But let's just try to get a good high-level understanding of what all this is about. Okay, so I'll briefly introduce why we need to do all of these things. Then I will introduce the necessary things for doing dependence analysis. Then I will talk about loop transformations, particularly transformations that are required for doing vectorization and parallelization. I'll also talk a little bit about, if time permits, we can also talk a little bit about exploiting locality in programs and so on. That's the high-level idea here. I have to say here that a large number of slides I have borrowed and adapted from various people on the net. So my acknowledgements is due to them. So in case you take my slides and use it for some purpose, please make sure that you acknowledge the original sources, because professionally that's the right thing to do, right? Okay, so what are we going to talk about? We're going to talk about dependence analysis, but then you might ask me, we have already talked about dependences, right? But we have talked about dependences for scalar variables. Now we are going to extend that to talk about dependences for array. And when you talk about array essentially consists of multiple elements, and then you're going to really figure out which statements are dependent on which other statements and through what values are they dependent, or through what memory locations they are dependent. So essentially, we are going to treat each element of the subscripted variable as different and then trying to find out the dependencies between them. Because if you try to analyze the array as one variable and trying to find out the dependence, then most of the time there is a dependence between every statement or the statement to itself, and it would not allow you to do parallelize, or it would not allow you to vectorize. I'll give you an example and then talk about it from that perspective. But you must understand that it is important to do this analysis at the individual elements of the array or the subscripted variables of the array, right? The focus is to, of course, exploit parallelism and to exploit better data locality. We might focus more on the parallelism aspect and leave the discussions for locality to a later point. And we will talk about the dependencies between the different statements within a loop, and how the loop needs to be ordered, or what is called the iteration ordering. We will talk about that. And if possible, and wherever possible, we will also talk about what loop transformations are possible and how those loop transformations can help us either exploit better parallelism or locality or other things, right? Yeah, so that's really the focus. Let's just start off with the simple definition of data dependence again. Here we will say that there is a dependence from statement S1 to statement S2 if both S1 and S2 access the same memory location, and if there is a feasible execution path from S1 to S2, right? There is a dependence from S1 to S2, and there is a path also from S1 to S2, and both of them are accessing the same memory location, but at least one of them must be a store in order for this dependence to be a meaningful dependence. That is, one of them must be a write, the other one can be a read, or the other one can be a write. Okay, this is pretty much the same definition that we saw for the scalar variable. But later on, we are going to probably augment this by saying that, okay, statement S1 in a particular iteration and statement S2 in a particular iteration, and then say that those two statements in those respective iterations, they access a particular memory location, and that could be one of the elements of the array that we are talking about. So that's how the simple, the data dependence that we talk in the context of scalar variables is going to be extended for doing array dependence analysis, or talking about array dependencies. Okay. So here is an example that we will talk about. So I have a nested loop here, and you could see that statement S1 writes to the array x of ij, array element x of ij, and similarly statement S2 writes to y of ij, and statement S3 again writes to x of ij. You can see that there is a dependence from statement S1 to S2, right, due to the variable xij, and this is a true dependence because whatever is the value of xij which is produced in the ijth iteration, right, that value is going to be consumed by statement S2, right, is going to be read by statement S2 and used in its computation. Therefore, there is a flow or a true dependence from S1 to S2. And this dependence happens because both statement S1 and statement S2 access the same array element x of ij, and they access the same element, in this particular case, in the same iteration I comma j. Right? Now let's look at one more example. Let me take the pen here. Right? Now let's look at this variable yij and this variable yij minus 1. Now if you look at it, right, in the ijth iteration, statement S2 is going to write in array element y of ij, and in iteration I comma j plus 1, right, that same element is going to be accessed by statement S1, because in the iteration I comma j plus 1, right, when you actually substitute those values, you will see that it is going to access y of ij. So there is a true dependence from yij to yi comma j minus 1, or there is a true dependence from S2 to S1, and this dependence is actually on two different iterations, right? One is ij, the other one is I comma j plus 1. That is also possible because in those respective iterations, they both access the same memory location y of I comma j. Okay, now let's look at this anti-dependence from x of ij in statement S2 to the statement S3. Again, this happens in the same iteration, right? Because they both happen in the same ijth iteration, and this is an anti-dependence. And of course, likewise, there is an output dependence also from S1 to S3. Right? Now you can see in all of these cases, we are talking about some memory locations being accessed by both the source and the destination of the dependence, right? And at least one of them is a write. Right? For example, we never talk about there is a dependence from this yi comma j minus 1 to this yi minus 1 comma j, because both of these things are real. So these two cannot be the source and destination of some dependence because of y. It may be because of other variables, but not because of y. Okay. Right? So we must also understand that when we talk about loops like this and writes to array variables and so on, each statement in the loop is actually executed n number of times, or possibly multiple number of times. In this case, if it is a nested loop, it's going to be executed n into n number of times and so on, right? And there could be dependence from the same statement to itself, because in a particular statement, I may be writing x of ij, and I may be reading some x of I comma j minus 1 also on the right hand side. So there could be a dependence from the statement to itself, right? And the data dependence can again be represented by means of a dependence graph, okay, where the nodes represent the statements and the arcs represent the dependencies between them, right? And we will now also talk about whether these arcs talk about loop carried dependencies or loop independent dependencies, right? I will give you examples of that, and we will also talk about what is called lexically forward and lexically backward dependence. Okay. But before we go and talk about all of these things, let me just introduce some notations here. We're going to use the notation iteration vector and iteration space essentially to talk about the different the different index values, right, that the loop can take. That's essentially what is called the iteration vector. For example, if you have a loop nest consisting of n loops, right, then of course there are these n index variable I1, I2, I3, In, and they can take values from maybe from 0 to n, 0 to whatever, right? And now if you can form a vector out of that corresponding to which iteration you are executing, right, then that's essentially what we call as the iteration vector. For example, in a two-way nested loop, when I say that the ijth iteration vector, it represents that the outer loop is executing for the ith time and the inner loop is being executed for the jth time, right? That's essentially what we mean by the iteration vector. Iteration space is the set of all possible iteration vectors. I will give you diagrammatic examples for all of them so that it becomes clear, right? So maybe what I should do is I should talk about these two things before I go to hunting. So let's think of this simple for loop here, right? Let me just go back to this one. And let's say n is 100 in this example, right? Then the iteration vector, if you're talking about this as, right, the iteration vector could be anything from 1, 1 to 100, 100. Right, that's essentially the iteration vector. For example, 5, 15 is an iteration vector. 20, 3 is an iteration vector, right? Because that corresponds to I value of 20 and j value of 3. So you're essentially talking about executing these statements for I value of 20 and j value of 3. That is iteration vector 20, 3. Right? That's what we mean by iteration vector. The set of all iteration vectors, as I said, from 1, 1 to 100, 100. If you write all of them, right, that is the iteration space. That's the space in which we are going to be iterating, right? Lastly, we will also discuss what is called the lexicographic ordering. And the lexicographic ordering is very simple. Basically, you just talk about some ordering between the vectors, right? Let me just hide this so that you could see the slide. Yeah, I'm sorry. What happened? Okay, all right. So, for example, if I take two iterations vector 1, 3, 2 and 3, 1, 1, then obviously 1, 3, 2 is earlier than 3, 1, 1, right? And similarly, 1, 1, 2 is earlier than 1, 1, 3. This idea is what is being captured in this formal way in this statements over here, right? Again, let's not worry about it. All of you know what is lexicographic ordering or dictionary ordering. When it is extended to vectors, right, we basically understand what that means. Okay, now again, take the same example here, and I have taken for the I loop, right, values from 1 to 4, and for the j loop, I have taken values from 1 to 6. And you can see that some specific iteration vectors are 1, 3 or 4, 2, etc. And right, the iteration space is essentially from 1, 1 to 4, 6, right? And we are assuming that the I dimension goes this way and the j dimension goes this way. So this is 1, 1, 1, 1, 1, 2, 1, 3, 1, 4, 1. And if you go all the way up here, this is 4, 6. And in this particular case, the iteration, right, the outer iteration is I and the inner iteration is j. Therefore, the iteration order is something like this. You go for all the values of, you go for one value of I, you cover all the values of j, and then come back and then go to the next value of I, and then cover all the values of j, and go so on and so on, right? These blue arrows and red arrows here essentially represent some kind of dependencies that are there in this particular loop, right? For example, here, each of these blue arrow in this particular example talk about a particular flow dependence, and the red arrow talks about an anti-dependence. So you can see that these horizontal blue arrows, right, correspond to the fact that there is a there is a 1, 0 dependence that you would see in here. For example, there is a yij value that is being written in by the statement S2, which is going to be used by S3, right, in one I iteration later, right? So that is basically this blue arrow. Similarly, there is a 0, 1 dependence here, which is coming because of this dependence. Okay, you can see that yij, which is being produced, is being used by statement S1 in the iteration I, j plus 1, and that dependence is essentially this blue arrow. Okay, You can also see that there is an anti-dependence that we talked about, right? That's anti-dependence, okay, is essentially from, let's see, which anti-dependence are we talking about? Yeah, I think this one, right? Between this xij and xi comma j plus 1, which is basically a 0-1 anti-dependence. That's essentially what is represented by this red diagram. Again, don't worry about some of these vectors that I am talking about. I will talk about them in some level of this dependence vectors that I am talking about. I'm going to introduce them in one of the later slides. Okay, so at this point in time, what you need to take is that each one of these points is a point in the iteration space, and these arrows, blue arrows and red arrows, essentially talk about dependencies between these iteration spaces, which are caused because of these array elements accesses in between them. Right? That's essentially what we are talking about. So, for example, to say that this particular iteration point or this iteration vector, whatever that is, right, is going to depend on this computation for this iteration vector, computation for this iteration vector, and it also has to be done before this iteration, means before this particular point, iteration vector point is going to be executed. That's essentially what it's trying to say. Okay. Right. Now, again, we will now talk about the same example, but now try to explain this or try to represent this in the form of a data dependence graph. The data dependence graph, essentially, in the data dependence graph, each node represents one statement in your loop. So we have basically three statements. There are three nodes, and you can see that there are dependencies between statements depending on whether there is a dependence between those two things. For example, there is a dependence from S1 to S2 because S1 produces the value x of ij, which is being consumed by S2. So there is a true dependence from S1 to S2. Similarly, there is a true dependence from S2 to S3 because S2 produces a particular value of yij and S3 consumes that value. It probably consumes it one I iteration later, but still there is a dependency. Right? Similarly, between S2 and S1, there is a dependency because of this yij and yi comma j minus 1. Right? And this anti-dependency is from S3 to S1. I'm sorry. That seems to be something wrong here. What did I miss? Yeah, this seems to be something wrong here. We'll come back to that later. Okay. So now, as I mentioned earlier, we're going to talk about these dependencies, but not just dependence from statement S1 to statement S2. Now we are going to say statement S1 on iteration I, which is the source of the dependence, and statement S2 on iteration J, which is the sink or target of the dependence. And now we say that both S1 and S2 in the respective iterations I and J access the same memory location, right? And one of them is a write. Then, of course, you say that there is a dependence from S1 to S2. Okay? And we talk about something called a distance vector, which is basically the difference between the index vector of the destination minus the index vector of the source, right? So if you just take this iteration vector and then subtract it from this iteration vector, and then subtract this iteration vector from that, then you get the distance vector. Okay, and mathematically this is represented by this, and you can see that the distance vector is also represented or can also be represented as a direction vector, where you use less than sign if the distance is positive, you use equal sign if the distance is 0, and greater than signs if the distance is negative. Again, we will take the same example and then try to see what these values are, right? Okay, so here is another example, a little bit more illustrative. Let's look at this. So here I have a three-way nested loop, right? And there is only one statement here. Therefore, the dependency is from S1 to itself. And you can see that this statement really produces a value and writes it in location I plus 1 j comma k, and then in some subsequent iteration, right, that particular location is likely to be accessed. So let's look at two different iteration vectors here as an example. For example, if I take the iteration vector 3, 8, 6, that means substituting I is equal to 3, j is equal to 8, and k is equal to 6, then the left-hand side for this iteration vector would be 4, 8, 6. That means that it would produce the value of array element 4, 8, 6. Then if I take some other iteration vector, let's say 4, 8, 5, right, and then look at on the right-hand side, right, that is being consumed by, right, consuming the same memory location 4, 8, 6. Therefore, we can say that from statement S1 in iteration 3, 8, 6, there is a dependence, and this is the producer of the dependence, and the consumer of the dependence is this one, or the destination of the dependence is the same statement, but for iteration vector 4, 8, 5. And this actually holds for various such values, not just for one of them, but for various such values. And therefore, if you try to capture this dependence in terms of some kind of a vector, it essentially tells you that the distance between these two iteration vectors is basically 1, 0, and minus 1, right? That's what we call as the distance vector. This is probably easier to understand than the definition that I gave in the earlier slide. In other words, what we are trying to see is that you are trying to identify the source and destination of a dependence, and between the source and destination, you are also going to say on which iteration vector of the source and on which iteration vector of the destination, right, they access the same memory location. We have already verified that one of them is a right. Now what you are trying to do is that you are trying to find out the difference between the destination's index vector minus the source's destination vector, right? And when you do that, you have this distance vector 1, 0, 1. So now you can say that for any value ijk, right, there is a dependence from S1 to itself, and the distance is 1, 0, minus 1. That means that statement S1, when it is executing for, let's say, ijk, is going to produce a value which is going to be consumed by the same statement in iteration I plus 1, j, and k minus 1. Right? That's essentially what is going to happen. And that's exactly what's happening here. Right? I plus 1, j, k minus 1. Right? So that's the idea of distance vector. The direction vector essentially says that if the value is, right, equal to 0, you put equal. If the value is greater than 0, you put the less than sign. And if the value is less than 1, you put the greater than sign. Right? And we call this as positive. That is, whenever it is positive, right, the dependence is positive. And right, so right, if it is so sorry, let me put it this way. So the distance vector, right, for it to be legal, has to be always positive, lexicographically positive. That means that it must be greater than 0, 0, 0. Right? That means the first non-zero component in the distance vector has to be positive. That is, you can have 0, 0, 0, 1, or you can have 0, 1, 0, or you can have 0, 1, minus 1, or you can have 1, minus 1 plus 0. I'm sorry, 1, minus 1, 0, whatever you want. But the first non-zero component in the distance vector has to be positive. That is when there is a dependence. Remember, the dependence essentially says that both S1 and S2 access the same memory location, and there is a path from S1 to S2. Right? And this path is also inclusive of your iteration vector. So S1 in iteration vector I and S2 in iteration vector j, there is a path from S1 of I to S2 of j, correct? And that is why, and in order for that to be satisfied, this distance vector has to be lexicographically positive. Right? If it is not lexicographically positive, then the dependence would not be satisfied. That's essentially the idea. Okay, so there is one more example here. This is a little bit more tricky, where I have a nested loop, right? But it's in that nested loop, I am accessing a one-dimensional array, right? And if you look at it, I have taken different iteration vectors like 3, 0, 3, 1, 4, 0, 4, 1, etc., right? And you can see that each one of this is essentially producing a value for a of I plus 1, which is consumed in the subsequent iterations for all iterations of j, right? So here, the distance vector, if you see, the distance vector corresponding to these two would have been like 1 comma minus 1, right? 1 comma minus 1, whereas for between these two, let me take the pen so that I can say. So if you look at the distance vector between these, I'm sorry. Yeah, between these two, if I look at it, right, the distance vector would have been 1 comma minus 1. Whereas if I look at these two, the distance vector would have been 1 comma 0, right? But in general, it actually holds for all values of j. Therefore, we say that it is 1 comma dash, or we can also put it as a star, right? So the direction vector is less than comma star. That's essentially the idea. Okay. Let me just see. I will make sure that this is correct. That's definitely S3. Okay. Yeah, sorry. Okay, I got it. Okay. So now let's go back to the same example and talk about the dependence distances, right? Now, as I mentioned earlier, let me again take my pen and then show each one of these dependences and make sure that you understand them. So there is a dependence from this x of ij to this x of ij, right? So that is the dependence from S1 to S2, and this dependence is within the same iteration vector, that is from ij to ij. Therefore, the distance between these two iteration vectors, the source iteration vector and the destination iteration vector, is 0, 0. That is why you have this as 0, 0, right? Let's now look at this other dependence from S2 to S3, which is over here, right? Now, S2 produces a value y of ij, right, in iteration I comma j, and that same value is going to be consumed by S3 in iteration I plus 1 comma j, right? And the distance between I plus 1 j to I comma j is 1, 0, and that is this distance vector, right? And now you can also see that there is a dependence from S2 to S1, which is essentially, let me just mark it as, mark it in a different colors, right? Let's take blue and just mark it like this, and the one over here, right? So you have this dependence, and this dependence is essentially whatever value that S2 produces in iteration I comma j is going to be consumed by S1 in iteration I comma j plus 1, and that is this dependence 0, 1, right? Now let's look at this anti-dependence, which we are getting confused when we were discussing that in the last time, which is again between this and this, right? You can see those two things, right? The value of x of ij plus 1 has to be consumed, right, in iteration I comma j before, right, before statement S1 writes on to it. Statement S1 will write on to that same location in iteration I comma j plus 1, right? So this will write into this location in iteration I comma j plus 1, but the value is being read by S3 in iteration I comma j. Therefore, there is an anti-dependence from S3 to S1, and that is at a distance 0, 1. Okay, so let me just stop here for a minute and then see whether this was understood or whether you people have any questions on this. If you can just understand the dependence distance, that is important. That's actually required for the rest of the discussions, right?
Sir, I have a question.
Yeah.
So what determines the direction of this dependence, the arrow direction?
Right. So you can actually see that when you are executing this loop, right, how exactly is the flow of dependence going to be, right? So for example, it's very easy to see why it is from S1 to S2 because that's the order in which you are going to execute this loop, correct?
Correct.
And let's now look at S2 to S1. Why do we say that this dependence is from S2 to S1 and not the other way around? Right? You can see that it is going to produce a value in ijth iteration, correct? And then in a subsequent iteration, I comma j plus 1, which is lexicographically greater than I comma j, right? And that is why you write this as from S2 to S1.
So can you also explain about S3 to S1?
S3 to S3 to S2, is it?
Yes, S3 to S1.
S3 to S1. Okay. So this is the anti-dependence that we are talking about, right? Here a value has to be consumed from location x comma I plus x comma x of I comma j plus 1 before that location is being rewritten. Right. For example, let us say I is equal to 5 and j is equal to 6. So you are talking about a location 5 comma 7. Right. So when you are reading the value x of 5 comma 7, right, in iteration 5 comma 6, that same location is going to be overwritten, right, in the next iteration 5 comma 7. Therefore, there is this anti-dependence. That means that this read must complete before this write.
Okay, sir. Makes sense. Okay,
yeah.
Thank you.
And all of these dependencies have to be lexicographically greater than 0. You can also see that. Right? This is greater than 0, 0. This is greater than or equal to 0, 0. This is greater than 0, 0. This is greater than 0, 0. Right?
Yes.
All dependencies have to be lexicographically positive in order for them to be honored. Right? If the dependence happens to be lexicographically negative, then that is a invalid ordering of the loop. Okay, so let's just go forward. The same dependence distances are now represented in the form of direction vectors. Again, I don't want to confuse you with the too many notations. We will often interchangeably use them, but again, you can always see that if the value is positive, right, you use the less than sign. If the value is 0, you use the equal sign, right? And the value is quote unquote many values, you will actually use the star. Okay. Now, we will also talk about these dependencies being loop independent or loop dependent. Let's just take the same example here. Because this dependence from S1 to S2, right, is from the ijth iteration to the same ijth iteration, we call this as the loop independent dependent. That means it happens in the same, right, iteration for the same iteration vector. Whereas when you have this kind of a 0, 1 or a 1, 0 kind of a dependence, that's essentially what is called loop carried, because it goes from one loop iteration to some other loop iteration, right? That is essentially what is being captured here in terms of formal definitions. So if S1 in iteration I and S2 in iteration J access the same memory location, and there is a dependence from S1 to S2, and if I happens to be exactly same as J, therefore J minus I would be 0, 0, that is called loop independent dependence, right? And loop carried dependence is that if that is not the case, and of course J is greater than I, right? And it has to be greater than 0. That's essentially what is called the loop carried dependence. Okay, the forward and backward does not really matter too much for our discussion, so let's just skip that. But okay. Now let's talk about several loop transformations. I will actually give you examples of these loop transformations, and we will also talk when these loop transformations are legal. All right, there are these different loop transformations that we're going to talk about. The first simple loop transformation that we're going to talk about is loop unrolling. Right? We already saw how to do loop unrolling when we talked about scheduling for VLIW processor. For example, if I want to unroll this loop some number of times, maybe 2 times here, then what I can do is I can actually write something like this, right? Where the body of the iteration is repeated multiple times, once for each unrolling value. And of course, the index vector, the index variable is also appropriately modified. Okay, so you can see that this is basically loop unrolling. Loop unrolling is always valid. Only thing that you have to be careful is that when you do loop unrolling, you have to make sure that you iterate exactly for that many number of times, right? So if the values are not exact multiples or whatever it is, then you will have a few iterations. For example, let's say that the original loop, right, has to iterate for 8 times, 1 to 8, and you are unrolling by 3, right? That means that you will do 2 unrolled iterations of 3 plus 3, 6, and then there is 1 remaining iteration which will do the remaining 2 iterations. So that has to be taken care of, and as long as you take care of that, loop unrolling is a valid transformation or a legal transformation in all places, right? Okay, why do we do loop unrolling? We do loop unrolling to increase the size of the basic block. Loop unrolling also removes some of the control overhead, and that's also beneficial. Now let's look at another transformation called loop peeling. Now let's look at this loop and now try to react on this, saying that supposing, let's say, we have this loop and we also looked at vectorization or parallelization of this loop. The question is, can this loop be parallelized? Are there any dependencies that prevent this loop from being parallelized? Right? First of all, is there any dependence that we talk about? Yeah.
No, it's a constant addition to the entire vector.
Sorry, it's a constant addition?
Essentially, we are adding a constant to all the elements in the vector, right?
It's not a constant. Yeah, A1 may not be a constant, right?
Okay.
And A1 is also getting defined in the first iteration or getting written in the first iteration, right? That's really the key, right? For example, here, if you look at it, in iteration 1, A1 is being written. And in all subsequent iterations, the written value of A1 is being used. So if you look at it, there is a dependence from the first iteration to the second iteration to the third iteration and up to the nth iteration, right? And therefore, if you want to execute these iterations in parallel, it is not possible because there is a dependence from the first iteration to every other iteration. Therefore, this cannot be parallelized, right? Or this cannot be vectorized, whichever way we want to look at it. Okay? Because every iteration depends on iteration 1. But what you can do is that you can actually peel the first iteration out of the loop, right? Yeah, please please mute your mic. So what we can do is that we can actually peel the first iteration of the loop and rewrite this program in the following way, where A1 is written outside of the loop, A1 is equal to A1 plus A1, and then the loop only goes from 2 to n. Now, when you do this, right, now you see you're exactly getting what I think Aditya was saying, that every iteration you are actually adding one value A of 1 to it, right, which was actually defined outside of the loop, and therefore the different iterations of the loop, they are independent of each other. There is no dependence between them, right? The different iterations of the loops are independent of each other, and therefore they can be executed in parallel. This is what is called the loop peeling. You can either peel the first loop or you can peel the last loop. You will peel the last loop when you have array elements involving A of n kind of a thing, right? So this is a simple loop transformations which allows you to parallelize this thing. So when you can do this, you can actually vectorize the loop, right? You can actually make the second the for loop as a for all loop. Okay.